Good morning. Welcome students, teachers, and educators from the Pueblo community, and thank you for joining us today. I'm Nick Potter, Director of Community Relations and Development for the Pueblo City County Library District. Today we are live streaming from the Robert Hogue Rawlings Public Library. Each year, the Pueblo Library hosts the All Pueblo Reads project. All Pueblo Reads is a literary project designed to get everyone in Pueblo County reading and discussing one book at the same time. This year, for the first time ever, we are featuring a cookbook. The selected book for 2021 is Ottolenghi Flavor, a cookbook by internationally renowned chef and author Yotam Ottolenghi. The All Pueblo Reads Youth Companion Book is Science Experiments You Can Eat by Vicky Cobb, which some of you may have already read or are currently reading in your classroom. Vicky Cobb is the well-known author of more than 85 highly entertaining nonfiction books for children. Ever since 1972, when HarperCollins first published Science Experiments You Can Eat, Cobb's lighthearted approach to hands-on science has become her trademark for getting kids involved in experiences that create real learning. It is no surprise that she is known as the Julia Child of hands-on science. Currently, she is becoming increasingly popular as a speaker to children and adults as educators seek out sources for materials and activities that promote learning in the classroom. Today's popular buzzwords in education include hands-on science, experimental learning, outcome-based, multidisciplinary, and critical thinking are all words that are embodied in Vicky Cobb's work. Vicky Cobb credits her outlook on education to her mother's forward thinking. From kindergarten to 6th grade, she attended the Little Red Schoolhouse in Greenwich Village. Her early education was a joyful experience of hands-on activities, field trips, reading children's literature and not textbooks, creative projects, and a kind of portfolio evaluation that today's educators realize are the most powerful tools for producing individuals who have a lifetime love of learning. Vicky Cobb graduated from Barnard College with a major in zoology and went to get a master's degree in secondary science education. After early careers as a laboratory researcher and science teacher, she became a full-time writer of science books for children. Her book, Light Action, Amazing Experiments in Optics, represents her life as both an author and parent. Her co-author is her son, Josh, an optical engineer, and the illustrator is her son, Theo, an artist and art director. We have a very special program for you today, and I hope you are very excited about it. In just a moment, you will interact with author Vicky Cobb and learn many things about science, reading, and even poetry. Her program, Discovery, Why Scientists Love Science, will encourage you to experience how scientists think, the limits of their own perceptions, and the coolest thing that you'll learn today, in my opinion, is learning how to light blood on fire. Very Halloween, very gruesome, so I hope you enjoy it. You will also have the opportunity to ask her questions during the program. Teachers and students, please type your questions in the chat section of the program, and your questions will be read and answered by Vicky. Again, everyone, enjoy today's program, and please help me welcome award-winning author Vicky Cobb.
Thank you, Nick, for that wonderful introduction. I am really happy to be interacting with Colorado. I was a die-hard skier and spent many weeks in winter in Summit County. I have to tell you, Denver to Summit County, skiing your wonderful slopes. I live in Greenburgh, New York, which is just outside New York City. And I'm going to do a different kind of program. I'm not going to talk about the food very much until the end, but I'm going to ask you, since this is live streaming and I like to do an interactive program, I'm going to ask you a lot of questions, and all you have to do is just sort of say your answer under your breath. You don't have to raise your hand or anything, but I want you to stay engaged. And when I ask you to try something, I'll give you instructions, and you can try it in your seats, and I'll give you time to a few seconds to get the full experience. So I'm going to start with a little PowerPoint that I have. So I have some pictures that will illustrate what I'm talking about. So I have to get rid of this thing, share screen. And I'm going to get this from the beginning. One second. Can you see that? There I am. Okay. Now I want to have control over this, so I'm going to stop this. Okay. It's going faster than I wanted to do, so I'm going to just stop for 1 second and come back to this. Sorry about that. Okay. So as you heard, I had a wonderful education, and what I've taken away from that is I don't write for children. I write for one kid in particular, someone I know very well. I figure if this kid likes my books, then you might like my books. So here's a picture of her. I bet you can guess who she is. So this is me, and I am, you can see that. And one of the reasons people ask me how old I am, I always say I'm 11, because the year I was 11, I was in 6th grade. It was the best year of my childhood because I discovered so much about myself. And one of the things I discovered about myself was that I could write poetry. And you wouldn't think a scientist would write poetry, but I don't know, I just like doing it. And here's a poem I wrote when I was in 6th grade, and it sort of reflects my thinking at the time. It's called A Boring Day. On a dreary, gray, cloudy day, there's nothing for me to do or play. Why don't you dance, my mother says, or cook a meal, or make the beds, or read a book, or play with Ellie. And if you're hungry, eat bread and jelly. Play the piano or brush with your hair. Don't just sit around and stare. I can name hundreds of things you can do. I know that, I say, but I don't want to. And here are a number of books that I have written in the time since then. So I hate to be bored. And one of the things about writing is that I write something called nonfiction. I write about the real world because I think the real world is more interesting than anything I could possibly imagine. So when I write, I have to do research before I write. So every experiment that's in my books, I have done, and every place I write about, I have been to. So I did a series with an Alaskan artist named Barbara LaValle, and we traveled all over the world. And we did, I think it was 7 books altogether. This place is cold, is about Alaska. This place is wet, is about the Amazon rainforest. And this place is wild, is about East Africa. So we went to East Africa, and here's a map that shows where the continent of Africa is. And we did a lot of trekking. We went into the jungle, but we actually went gorilla trekking. And in order to go to gorilla trekking, we had to go down on the west coast of that Lake Victoria, which is sort of on the border of Kenya, Uganda, and Tanzania. And when we went down on the border, the Ugandans had drawn a yellow line across the road and put up this structure so people could take a photo up and have their picture taken at the equator. And on our way south, where we were going to go gorilla trekking, I told our guide that I had to be at the equator at exactly 12 noon the next day on our return trip, because there was a picture I wanted to take. And you know, one of the ways you get information is you take a picture. So I'm going to show you the picture that was taken at the equator at 12 noon on the next day. Here I am with Barbara. And you'll notice something very unique about this picture. Since you can't tell me what you see, I'm going to have to tell you what's in that. If you look near our feet, you will see that our shadows are very, very small. So if you want to, raise your hand and point to where the sun has to be in order to make that very, very small shadow. It should be directly overhead, shining straight down on the tops of our heads. And the only way to make the shadow smaller is to go to Weight Watchers or something like that. And it tells you two things. It tells you where I am and what time it is. 12 noon on the equator. I wrote books, many books that ask questions. Scientists ask a lot of questions. And so I'm going to take a question that I put in this book, and we're going to spend a little time answering it. How do we know the Earth is moving when it looks as if the sky is moving? How do we know the Earth is moving when it looks as if the sky is moving? Well, you can have an opinion about the question. One kid says, of course the Earth is moving, everyone knows it. And then another kid says, I'm only interested if a moving Earth gives me a good ride, and so far I don't feel it moving. And another kid said, who's into watching the sky anyhow? I can't do anything about the objects up there, so why should I care? Dumb. But meanwhile, this girl is reading a book about how everything affects you. So the reason that we think that the Earth is not moving is because everything in the sky is moving, and we watch the sky. So I'm going to show you the picture that people about 700-800 years ago drew of the Earth and various objects in the sky. Now, what you see in the sky is you see the sun rises and sets every day. The moon rises and sets every day. The stars rise and set every day. And then there are these other bright bodies that also seem to move, but every once in a while, they move backwards. They seem to be going in one direction, then every once in a while they sort of stop and move backwards for a little while, then they move forwards again. And they call them planets because they seem to be wandering. They didn't have the same set path. But if you started watching a planet like Mars on a particular day of the year, and you followed it every single day, sooner or later, it would come back to the exact spot where you first started watching it. So everything moved in a circle around the Earth. At least that's what they thought. And they had an excuse for why they think that the planet moved backwards. It seemed to have a separate kind of what they call an epicycle. It made a separate circle on its orbit. And as a result, that the motion of the planets made a pattern like curlicues. And of course, people watched the sky a lot because didn't have a lot of light competing with it. And when you think about it, they had to figure out what was happening in the sky from the only two things they could see: motion and light. That was it. Those are the things they had to work with. And they made a lot of measurements because they used it for navigation. And there was a man who lived there at that time. His name was Copernicus. And he wasn't really an astronomer, but he looked at all the measurements of all of the motions of the planets. And he said, this doesn't really make sense to me because of those curlicues, those epicycles. He said the whole thing would be a lot simpler if you put the sun in the center and you had all the planets orbiting the sun. Because we know something is moving, but we don't know what is moving. So let's say the sun isn't moving, but we're moving. That was a very, very, very radical idea. And his assistant said to him, Nick, you really have to write a book. And Nicholas Copernicus said, no, I'm afraid no one will believe me. I have no proof. but he knew what the proof would be. So I'm gonna show you a way you can learn about that. Now, how do I have to get out of this thing? Okay, so there we are. So we use our senses to learn about the world we live in. But our senses are not always reliable. Sometimes we see things as they are not really in real life. So I'm going to show you something that's called an illusion. What I want you to do is take your finger, your index finger, and put it about a foot away from your nose, and open and close each eye as you look at your finger, and see what happens to your finger as you open and close each eye. Your finger appears to move. You're going to compare your finger to the background behind it. And you will see that your finger shifts depending on which eye you look at compared to the background behind it. Now, this is a name for this. We have to give things a name when we talk about them. It's the name of this phenomenon where the foreground shifts compared to the background, depending on the angle of the observer. And the name for that is parallax. So what you're looking at here is ocular parallax, because it refers to your eyes. Copernicus believed that parallax would prove that the Earth is moving, but he had no proof. And the reason he had no proof is because he knew the distances were too big and the differences were too small. But here is, let me see if I can get this to start sharing again. Here is the definition of parallax. Now, we're going to look at, this is one of the patterns in the sky is called a constellation. This is a very common constellation. It's called the Big Dipper. It has 7 stars in it. These 2 stars are called the pointer stars because if you follow them up, they point to the North Star, which is at the top of the axis of our rotation. But there's an assumption you have to make about this Big Dipper. They're not all the same distance from the Earth. Some of these stars are going to be closer than others. So let's imagine here's the sun and the Earth is rotating around the sun. And you see, here we are. Let's say, what is today? Today is the 21st of October. And we're looking up in the sky at the Big Dipper. And we're going to see that the pattern of the 7 stars. And then in 6 months from now, so what's 6 months from October 21st, November, December, January, February, March, April 21st, we're going to be over there. We're going to look at the big picture again. And go back here. And you're going to look at the Big Dipper again. And the question is going to be, are the stars in exactly the same place as they were tonight and as they're going to be 6 months from now? And the answer is no, because we're going to have this distance from the Earth where we are tonight to 6 months from now, we're on the other side of the sun. So it's going to have a different look, and that the stars will not be exactly aligned. And this is called stellar parallax. And Copernicus would believe that this would prove that the Earth moved around the sun. Well, rotation, night and day, is created by 2 kinds of motion. The Earth is also spinning on its axis. So that's what creates the motion of the rising and setting of all and day and night. So he wrote his book. And this is a picture of his book, and he explained everything in it. And everybody, there were science deniers then. They didn't want to believe it. And it was banned. And some people even got killed for reading it. A very old book. But I'm going to show you this picture of stellar parallax. Let's see if I can get it to, I'm going to get out of this. I have to close this. This screen. How do I do that? I'm going to stop sharing, and then I'll get rid of this. And I'm going to show you this video, which is showing you the motion of the parent Earth against the stars. This is an example of what happens to stellar parallax. It's a very nice video. It's sped up a lot. You see. Let's see. Okay, so here it is. It's on the web, but I'm going to turn it on, and you can see that as you look at the Earth turning, you're going to look at the background of the stars, and you will see that they are moving very, very, very slowly as the Earth spins and as it moves in its orbit around the sun. And now we can make those measurements because we have very, very good instruments that can measure it. So I bet you can go home tonight, and when you ask your parents, how do we know that the Earth moves around the sun? This is going to tell you how we know that. Okay, so
you ever wondered what actors and actresses do when they have to get?
Oh wait, I have to get rid of this. How did that happen?
Because I can promise you, it's not this.
Okay, so that was an interruption by my screen. I didn't mean that to happen. So I'm going to show you another illusion. There's a man who lived about 6,000 years ago. His name is Aristotle, and he was very brilliant. He lived in ancient Greece, and he thought a lot about the senses. He was the first person to ever name the 5 senses. So you have the sense of vision, hearing, smell, taste, the chemical senses, and touch. And of the 5 senses, he was concerned with what was real and what wasn't. So Aristotle said that of all the 5 senses, the one that was most important for knowing what was real was the sense of touch. But I told you, you shouldn't always trust your senses. So now I'm going to show you a very interesting illusion that is a touch illusion. It's called Aristotle's illusion. What I want you to do is I want you to take your 2 fingers and cross them like this. So your middle finger is on top of your index finger. Now take both your fingers, put them on the tip of your nose very lightly, close your eyes, and run your fingertips up and down the tip of your nose. And you should feel 2 noses. Do you feel 2 noses? I feel 2 noses. I even know the whole thing about this illusion. And I still feel 2 noses because you have been conditioned to feeling things with your 2 fingers that are next to each other with your fingers not crossed. And when you cross your fingers, one part of your brain doesn't know your fingers are crossed. Another part of your brain does know your fingers are crossed. But one part of your brain doesn't know. And as a result, you feel 2 noses. So here's another interesting fact about your sense of touch. Let's have a race to the brain, because what's happening is you're getting something called sensation at your fingertips. Your fingers are having pressure put on them. But then what happens is the message travels from your fingertip all the way up to your brain, and then your brain interprets the message, and that has another name. That's called perception. So sensation leads to perception, and you can confuse your perception. Here's something interesting. How fast does that message go? So let's do this. Everybody tap your 2 fingers together, like 2 index fingers. Now what you're doing is you're making a sensation on each finger at exactly the same time. And bam, the messages go up each arm to your brain. They're going to reach your brain, same place where you have to perceive the message. Now, do you feel it more on one finger than the other, or do they feel about the same? In this case, they should feel about the same because you have 2 arms and they're about the same length. And the rate they travel, which is very fast, I can't remember, I think it's about 200 miles an hour, something like that. It's pretty fast. It's not like the speed of light, but it's fast. And you have a short body, so it gets there almost instantaneously. This should be a tie. Now try this. Tap your lip. Do you feel it more on your finger or more on your lip? Now, your fingers are very sensitive. There are lots of receptors. There are lots of nerves in your finger, lots of nerves in your lip also. So that's not really a factor. Now, I feel it more on my lip than my finger. Now, think about this. Which is closer to your brain, your lip or your finger? Your lip is closer. So the lip The sensation on the lip is going to beat the sensation from your finger by a fraction of a second, but nevertheless, the message that gets there first becomes the dominant perception. Now you can try, when you go to bed, take your shoes and socks off, you can try, try a race between your finger and your toe, or if you're flexible, you can try a race between your toe and your lip. What do you think? What do you think's going to win? Okay. Now, I'm going to show you, I want you to learn how to think like a scientist. And I'm going to show you how a scientist thinks. You're all going to be thinking like a scientist. And I'll give you some directions. So just say what you think. Doesn't matter if you guess right or wrong, but I'm going to do a demonstration. So the first thing we're going to look at is we take an object. This is an object, and we have to give it a name. The first thing a scientist does when they study something is they give it a name. So what is this? This is a bottle, right? And now we have to give it its properties. So what's it made out of? Made out of plastic. What color is it? It's clear, right? Now I'm going to give you some other information about this bottle. What does this tell you? It's empty, right? It's empty? Okay. So now we're going to do an experiment with this bottle. It's a very simple experiment. I have a little piece of yellow paper so you can see it. I've rolled it into a little ball. I'm going to put the little piece of paper right at the mouth of the bottle, like that. Now I'm going to tilt the bottle. Watch what happens to the paper. The paper falls. Why did it fall? Do you know the name of the force that made it fall? Begins with G. Gravity. Gravity makes things fall. Now here's something really important about gravity. Number one is something called a force. A force is anything that makes things move. I'm going to give you a very important rule about forces. Repeat after me. Every force has a direction. Can you say that? Every force has a direction. What is the direction of gravity on Earth? Can you point? Straight down. Gravity isn't always, gravity also has a force that goes up, but we're too close to the center of gravity on Earth. So for us, gravity keeps us grounded. It always goes down. So now we're going to go back to this bottle. And we're going to try to use a different force to get the little piece of paper into the bottle. We're going to use a force that has a horizontal direction. So I'm going to rest the piece of paper right at the mouth of the bottle, and I'm going to blow the piece of paper into the bottle. You think I can do that? Okay, I'm going to blow it in. Didn't go in. Surprise! You didn't get what you expected. Looked like a piece of cake, right? Let's do it again just to make sure. Oops, where'd it go? I may have to make another piece of paper. I can't find it. Anyway, so we got a surprise. We didn't get the answer we expected. So now we have to think. Why didn't the piece of paper, why couldn't I blow the piece of paper into the bottle? You're thinking about that? Why couldn't I do that? I'll give you a clue. I set you up. I asked a question. I said, is this bottle empty? Yeah, it doesn't have soda in it, or whatever you call it in Colorado, pop or whatever. I set you up, but it is not empty. It is full. What is it full of? Air. Okay. So you think that you can't see air. So you have to imagine air. You can feel it, but you can't see it. So when I blow into this bottle, I'm already blowing more air into a bottle that's overflowing. It's full of air, so it's going to overflow. It's going to take the piece of paper with it. But scientists, they get a surprise. You know what they do? They ask another question. So here's the next question. What could I do to this bottle so maybe you could blow the piece of paper into the bottle? Well, I'm going to tell you, I may have a lot of ideas. Does anybody want to put any guesses in the chat? What do you think you could do to this bottle? So maybe you could blow the piece of paper into the bottle. Nobody's giving. Well, you know, when I ask this question, I always get the right answer from the kindergarten. They say, well, if it's logic, if the air is stopping the piece of paper from going into the bottle, could take the air out. How can we do that? How can we take the air out of the bottle? Well, you know, scientists have to work with what they have. I mean, we have vacuum pumps. We could take air out of anything. But we don't have a vacuum pump. I have my mouth. I could suck the bottle. I could suck the piece of paper. Oh, blow lighter. Cut the bottom off the bottle. Oh, we are getting some. That's a very, oh, I'm going to show you something. Here's it. I cut the bottle. I cut the bottom off this. I'm going to show you how that works. This shows you when it gets boring, okay? So I'm going to blow that. See, that was a perfect answer. But that wasn't where we're going at. Less pressure by blowing not as hard. But you know, you're going to have to try that. Because I haven't got time. I want to show you what we're going to do here. I'm going to try and suck some of the bottle, some of the piece of paper out of the bottle. Some of the air out of the bottle. This is not working. Let me do this. I'm going to squeeze it. Okay, I'm going to squeeze it. Now we're going to do another experiment. I have to make another piece. I'll keep losing my little pieces of paper. They're flying all over my room here. Okay, so now I'm going to show you something, and this is where science gets so interesting. I'm going to rest a little piece of paper on the mouth of the bottle, and I'm going to pop the bottle back into shape. Which way do you think the paper is going to go? Is it going to go out or is it going to go in? We can take a vote. I wish I knew how to do that, but you can take a vote. But usually when I've done this before, it's about 50-50. Some people say it's going to go in. Some people say it's going to go out when I pop the bottle back into shape. Now, here's why I like science. I'm not going to tell you what happens. I don't have to. We're going to do it, and you're going to see what happens for yourself. That's one reason I like science. The second reason I like science is it doesn't matter whether you guess right or you guess wrong. The only thing that matters is that you learn something. So I'm going to pop the bottle back into shape, and you're going to see for yourself which way. Oh, look, they all think, look, I'm getting votes. So we all think in, we all think out. Okay, watch. Let's all count to 3. Watch the little piece of paper right here. 1, 2, 3. It went in. Now let's think about that. What I did when I squeezed the bottle was I made it smaller inside, so some of the air push the piece of paper out. When I pop the bottle back into shape, the entire room, the air pressure in the room, maybe I should do it this way, but the label is still on the top. The whole room blows the piece of paper into the bottle. So this gives us the idea that air has force. When moving air has force. So I wrote a lot of books. I sent Mr. Schwartz a copy of my book, We Dare You, which has actually a bind up of 5 books that I wrote in one book of all these bets that are based on science. So here's a bet. Bet I can keep a ball in the air for an hour without touching it. So I have to have a couple of props. Hang on one second. You do this with one of these hair dryers. And I'm going to get a ball. And this is a surprise. I bet I can keep a ball in the air for an hour. Now, I haven't got an hour, but you'll see if I wanted to keep a ball in the air for an hour, I could. Ta-da! Notice that it's spinning. Okay. Now, when you see a phenomenon like this, you want to play with it. So we have to ask questions. You think I could put two balls? You think I could put two balls in it? See if it hold up two balls? This is kind of fun. You know what? I noticed this is a very old hairdryer. This is a very old hairdryer, and I noticed that. Oh, where is it? Oh yeah, the front of it. You see, it's got a little groove in it. That's why it's spinning so much. It's been knocked around a lot, so it's not the greatest hairdryer in the world. So then another thing is, what happens if we change the shape? Now this is a closed curve. So let's see what happens if I put something that has a similar size, but has a different shape. We'll put it. Let's see if we can put an Easter egg in the hairdryer. It's not working. Let's try this bigger one. This stays in it, but it's not stable. I think I just noticed that this is a defective hairdryer, but let's try this. Thinking what'll happen to this? I'm gonna show you where that went. Okay. There. So you can have a lot of fun playing with this. There's another application I could show you, but it's in my video. I made many videos, about 60 videos of the tricks from this book. But if you want to make your own videos from the book's in the library, and you and your friends can make your own videos. There are lots. I think there are 287 tricks, and we've got about 60 of them made. I'm going to show you some of those videos now. But you'll see there's another trick where you use a leaf blower, and it's called blowing up toilet paper. And it's Halloween is coming. I shouldn't mention this, but you can TP structures if you use a leaf blower, a broomstick, and a roll of toilet paper. So I'll let you find that one on the website. I'm going to show you a couple of videos about yourself, and then I'm going to talk a little bit about the book that you all are going to be reading in connection with the cookbook. So the first thing I want to show you is about your own body. And this is, let me see. I'm going to just open this up. Full screen. This is a video called Foot Feet. You can try it. It means you have to take one of your shoes and socks off, but here we go. Okay, let's see if we can get my cursor over here. Okay, these are my grandchildren.
Foot Feet, starring Johnny and Jillian. Bet you can tell shoe sizes without looking at feet. Measure the distance from your elbow to your wrist. Johnny is using a ribbon to measure Jillian. Once you have the proper length, then you can compare it to the length of Jillian's foot. Surprise, they are exactly the same. If you're flexible, you can compare the length of your foot to the length of your arm directly. Here, Johnny is going to check out his dimensions. And then, of course, you can measure the size of your boots.
Okay. See, how do we stop sharing? So that's one measurement. Now, if you want to try that, give you a couple of seconds to try that one. Take your shoe off and measure your foot. Can I get some feedback? How many people find that it works for them? Anybody? hope you don't have laces. It slows things down. I'm going to try and get out of this. Okay, I'm going to show you another video, and this is about food and nutrition. This is a video that shows what's in a nut. It's called a nut case. And I'm going to get here. This will tell you something about nuts.
Bet you can toast a marshmallow with a nut. When you consider the high price of oil, you might not think it grows on trees. Surprise, it does. This is a nutty trick, but we are not crazy when we suggest burning a Brazil nut. Nuts contain oil, and a single-shelled Brazil nut burns long enough for everyone in the exposure group to toast a marshmallow or two. Since this trick involves fire, have an adult present before you begin. Stick a Brazil nut on the triangular pointed end of a metal can opener and place it in the center of an aluminum pan. Light a long candle or a fireplace match and hold it under the nut until it begins to burn. Then extinguish the candle or match. Wait until the nut is burning steadily before you toast your marshmallow. Under the nut.
Yeah, there's really nuts burning.
Oh, with a nice fire burning, everyone got a bamboo skewer and a marshmallow to toast. Does it taste roasted?
Okay, burn.
Okay, now I want to talk a little bit about the book that everybody's reading. I'm very honored that you're doing that. Science Experiments You Can Eat. First, I want to say that it's not a book you read. You don't read this kind of book like a novel. It is a book that has recipes or procedures in them, and you're supposed to do them. You're not supposed to just read them. But the thing that makes this book so successful, and its 50th anniversary of its first publication is coming up, so you see I'm really old. I've known this stuff for a long time, is that procedures are evergreen. What I did in my kitchen 50 years ago, if you follow the directions, you're going to get the same results I did. So what scientists say, when you say to a scientist, how do you know? A scientist can say to you, this is what I did. If you do what I did, you'll know what I know. In other words, you become the primary source. You don't have to be a witness. You know, historians, they want to know the truth. They have to interview a lot of people. They have to read a lot of people's reports, and then they have to figure out who's telling the truth. When you do science, you are doing it yourself. So this book, one of the reasons this book has been so successful and has lasted so long is it's not just a bunch of procedures. It's a course of study in science. I used what happened in the kitchen to go from simple things about matter, because we're studying matter, food is matter, and food makes changes. Any change is of interest to a scientist, what affects that change. But it goes from physics, the basis of all science, through chemistry, which is the nature of matter and combinations of matter and how matter interacts with each other and how energy interacts with each other, to biology, to how all of these sciences come together in living things. And then I've revised it twice and added more. I've added stuff about proteins. They are the most complicated molecules. The protein means first importance, and it's why we can have life on Earth. Without proteins, we couldn't have life. Then there are chemical reactions. What's a chemical reaction? So you have experiments to see that is the change that occurs in a chemical reaction always involves energy. How is that energy managed in living things? So we're not on fire all the time, because burning is a very important chemical reaction. And then it goes into nutrition, plants we eat, how we use microwave energy. I added that chapter. We didn't have that many microwaves when I first wrote this book, but I added a chapter when I revised it on microwaves. You can do some interesting experiments with your microwave oven. And then we go into microscopic life, microbes, because they're very important. Microbes are very important for cheese and yogurt and a lot of the foods we eat. I heard something interesting the other day that you know how smelly cheeses can get, and you think they're rotten, and they are rotten, because that's what microbes do. They rot stuff. That in Thailand, they don't have any cheese, so they think the cheese is disgusting. And then how do you regulate all of these chemical reactions in a living thing? That's enzymes and hormones. And then when I revised this the last time, I realized that 70% of the American diet is processed food. It comes out of their kitchens and their laboratories. So I was curious about what they do to food. I mean, we process food when we cook it. That's part of food processing, but there are other things that they do. They stabilize it, and they give it shelf life, and they protect its crispness, and so on. So that's some of the ways we eat. And of course, they've done studies, and one of the most interesting studies that I found was that, you know, human beings are hardwired to like sweet stuff. Human milk is sweeter than cow's milk, for example. But they have done studies in some of these food companies to find what is the sweetness level? How sweet does something have to be so that you crave it? You become addicted to it. And it's a lot sweeter than we're hardwired for. So one of the things the FDA has been debating about is if you look at cereal that you eat, they don't tell you on the list of ingredients that they add sugar to it, but they do. They want to hook you on sweetness. So we'll keep that in mind. That's one of these phenomena. And now, if anybody has any questions, I think we have a few minutes. And please put your questions in the chat. And let's see if I can answer some of them.
So while we're waiting for questions, Vicki, I was just going to see, I know earlier you were going to talk about blood fire as something that was exciting for us for Halloween. And so, yeah.
Okay, let me do that one. Okay, this is
great. Thank you.
This is a really cool experiment. This is called vampire fire. Thank you for reminding me. I got a little ahead of myself. Okay, so you can go to this website, which is called WeDareYouVideos.com, and you can see. You can just go flicking through a lot of these videos. They're a lot of fun.
Dracula didn't invent this trick, but he would have loved it. Bet you can make fire with blood. Since this trick involves fire, be sure to have an adult
I have to put that in.
Begin. You can get hydrogen peroxide solution at any drugstore. When you pour the hydrogen peroxide on a source of blood like red meat, you will see bubbles start to form. Lots of bubbles. Now for the gory part. The best source of blood is a piece of fresh liver. The kids are going to take the liver and put it in that dish and pour in the hydrogen peroxide and wait for the bubbles to form. Lots of bubbles soon cover the surface of the liquid. And now for the fire. Light a long bamboo skewer and bring the flame over to the foam on the top of the dish.
Oh,
Got some fireworks going on there.
vampire. Ooh, oh, no. It's burning it. Oh, it's messy. Ooh.
So that's vampire fire. So you can have some fun with that. What is one of your favorite experiments? Okay. This is a really interesting experiment. It's a very complicated experiment, and I had to put statistics in it. Statistics is a kind of math that evens out variability. You want to smooth out the data so you see what really is happening. It's called Baked Steak, a study of enzyme action. And you know that you can buy something called a meat tenderizer in the supermarket. So I wanted to know if it really worked, and if you put the tenderizer in with an acid or a base, would it affect how fast it worked and how well it worked? So the important thing was that I had to get a way to measure the tenderness of meat. So how are you going to do that when you don't have any instruments, you know? So I decided I would count the number of chews before somebody swallowed the meat. So I had to cut the meat up into individual pieces that were about the same size, and I had to have all these controls in the experiment, but I got amazing results. It's in Science Experiments You Can Eat. And when the book was reviewed by the Scientific American, they thought that they zeroed in on this experiment. So I thought that was a really important thing to figure out. And you see, that's where the creativity in science comes from, because you have to use what you have to make measurements. And I'm going to tell you a couple of disclaimers ahead of time. Number one, science is hard. You have to work at it. You have to think. You have to get your head into it. And you have to be good in math, because science is becoming increasingly dependent on voluminous amounts of data. We have computers now to help us process these data, but we have to be familiar with math. So if science intrigues you, and it's a body of knowledge that has been growing for 600 years now, and it grows by tiny little steps by individual scientists. It's like a wiki. Everybody contributes to the pool of knowledge. But then every once in a while, you get enough information that you get something big, like a law, like Newton's laws, the first law of motion, that a body at rest will stay at rest forever, and a body in motion will stay in motion forever, unless acted upon by an external force. Sounds like a simple law, but it took a long time to figure that one out. And by the way, I didn't point this out earlier, but one of the things that the ancient people noticed was that the motion in the sky was perfect. Nothing ever sped up, nothing ever slowed down. But motion on Earth is different. Everything slows down and ultimately comes to a stop. So figuring out why there was a difference between heavenly motion and motion on Earth was one of the great contributions of Isaac Newton. It wasn't obvious. Next question. How did you think of making the experiments? Well, to begin with, when I wrote Science Experiments You Can Eat, I already knew a great deal about food and processing food and the kitchen and measurement, because I was a pretty good cook in those days. Now I just get a meal together. I don't really cook. Although I did buy one of the cookbooks of your companion volume, the cookbook, and I'm going to do some of those recipes. Particularly, I'm interested now in updating Science Experiments You Can Eat with plant-based food. How can you make plants taste like meat? I mean, that's an interesting question. You get ideas just from living. You know, you look at what for example, in my trailer for the Science Experiments You Can Eat, I show you about boiling water. So a cook knows if you put water in a pot and you put it on a stove with heat, so if you wait a while, bubbles are going to come up. It's going to get hot. What is that? Scientists look at boiling water and they ask questions about boiling water. Okay, how hot does it get? So you stick a thermometer in it. You see it boils at 212 degrees Fahrenheit, 100 degrees Celsius. But then you notice something else. Once it starts boiling, it doesn't get any hotter. And there's another thing. If you boil water in Colorado, it's going to boil at a lower temperature. It's not going to be as hot if you do it in the mountains, and if you do it at sea level where I live. At sea level, my water boils at 100. I'm maybe 20 feet above sea level. Maybe I'm more than that, but I'm not much above sea level. So you see these differences when you measure and you look at things, and it gives you other ideas. The key thing is to think of another procedure, another thing you could do, another thing you can change that will give you more information. So I already had a whole body of knowledge about all this stuff. I just started asking questions that I could answer. So, next question. When did I write my first book? I wrote a lot of things before I wrote my first. I was a teacher and I became a mother very young. And I wanted to stay home with my kids and I still had to make money. So I saw an ad in the newspaper that invited teachers to write educational materials. I figured, well, if I could talk about science, maybe I could write about it, but I had no experience writing. So I interviewed for this job and I got a job to write a chemistry book. I knew chemistry, but I had to write it. He said, the guy who hired me said, it has to sound simple. So go home and write me a chapter. That's called working on spec. And I was pregnant at the time with my first son. I hate to tell you how long ago it is. His kids are all grown up now. But anyway, I wrote my first chapter trying to make it sound simple. And I took it back to him and he read it. He looked at it for about 30 seconds, if that long. He said, it's not simple enough. Write it again. I took it home. I rewrote it. And then I wrote it back. I wrote it back to him 3 times. And the 4th time he kept it. And then he called me and he gave me the book contract. And I wrote the book. When my son was then born and he was sitting in a little infant seat at my feet as I used a typewriter in those days. So that was my, but it wasn't published. He ran out of money or he had some kind of problems. It was a storefront, you know. I just always wanted to learn things. And somebody asked me if I could do something. I always said, let me think about it. And then I said, yes. I didn't turn down many opportunities to learn something and to grow. So that was 1964, a long time ago. Have you ever made any of your own? I've made them all. And some of them I've made up. Some of them I've done other people's experiments. One of the giants in the history of science, a woman, the first major woman scientist is Marie Curie. And I wrote a biography of hers, which is maybe in your library. And one of the things I noticed about when I was learning about her was that she couldn't wait for the mail to come because she got these journals where her colleagues that were also interested in the atom, where they were doing experiments, and she would grab these journals and she would race into her laboratory and she would repeat other people's experiments. Because when you do them, you may alter the procedure a little bit. You may see something somebody else didn't see, but that's how you build consensus in the scientific community. And one of the very great things about COVID, I just read this book called The Code Breakers, the story of the woman who won the Nobel Prize because she had the lab that understood how to make RNA. She understood how to synthesize the genetic material. And her lab was the one that made the first test for COVID. And the first thing that she did was she went to the chancellor of the university I think she's at Berkeley, where she worked. And she said, we have to waive our rights to proprietary property. Anything we discover has to be for science, has to be to save humankind. So these drug companies, they all get their own little proprietary things. They want to keep it a secret so they can make money with their information. But we didn't have time for that with COVID. Everybody shared their information. These young scientists, I don't live far from Regeneron. I know a lot of the scientists there. They were so excited. They dropped everything and they shared their raw data. And that's one of the reasons that we had such incredible collaboration and teamwork, which is the way Marie Curie and her husband imagined science could save the world. Instead of everybody, there's only one nature to be discovered. We should share it and see where it takes us.
Mrs. Cobb, Vicki, thank you so much for joining us today. I really, really appreciate it. And I know that our classrooms that are participating really appreciated it. We had a couple of classrooms that needed to leave because it was lunchtime, and we never want to get in the way of children eating. So
Right.
yeah, so they did want to let me know that they love science and they loved your presentation. So thank you so much for joining us today.
And if anybody does any experiments and they have any questions, you can give them my email, which is the word email at vickycobb.com, and you can and they can share their information, and I promise I will respond to it. So
great. That's very nice of you to respond to them, and we will. For those of you that attended today, and for those of you that requested classroom copies, we will send an email that has all of the videos that Vicki shared today, as well as the recording of this video, as well as Vicky Cobb's email address, so you guys can ask her questions directly.
Don't keep that recording in circulation too long, please.
No, we won't. Yeah, it won't.
Okay. Thank you. Thank you. Okay, it's a pleasure, and I'm very honored again that you bought so many of my books. My publisher will be surprised. Happily. Okay, bye-bye.
And thank you all so much for joining us this morning. I hope you all had a lot of fun and learned something new about science. This program, again, is part of the All Pueblo Reads project for 2021. We have a ton of great programs for adults and children, so please visit the Pueblo Library's website or follow us on social media for all of the fantastic programs that we have going on this year as part of the All Pueblo Reads project. Thank you for joining us, and have a great day.